is forming a needle-like structure, and the sharp tip is a stress concentration, and it will produce stress concentration, and it will cause a crack formation, a crack initiator, and the next is a crack formation, propagation, and so forth, the failure. All right. So that's the reason we need tempering. Okay, it's just the post-processing, meaning that it's require a heating and cooling process. Okay, right after the quenching, cooling. Of course, after quenching, we cool it to room temperature, and then we do the reheating process just to reduce the brittleness. Okay, and increase the toughness. How the toughness can increase? Because this one is already reduced. Okay, so remember the graph of a stress strain curve. Okay, if we sketch the brittle structure, it will fail without plastic deformation, and the area under the curve is small. This is defined brittle. Plus, less, or low toughness. Okay, through the graph, we can interpret that it is failed within the elastic region, less plastic deformation, and the area under the curve is small, showing less energy absorption. Okay, so therefore, we want to eliminate the brittleness. If we compare between these two, okay, so this show area under the curve larger compared to the first one, or maybe not like this. Practically, it's maybe for the after heat treatment process, after tempering process. Okay, maybe the tensile strength slightly higher than fracture strength of the brittle material, but the area under the curve is larger. Okay, and then for the green one, it is high toughness. Okay, and less brittle. Why? Because it's failed after the it shows a plastic deformation. Therefore, toughness is associated with the brittle, ductile fracture. Okay, it will show some what we call it reminder or signal. Okay, by showing some changes in the dimension of your component or any engineering component. If there is a plastic deformation, meaning that, for example, let's say the vessel, okay, vessel, and you put high pressure inside the vessel, okay, pressure vessel, and inside the vessel, you know there's a high pressure, so the way you monitor the safety of the pressure vessel by measuring the thickness of the vessel. Okay, if you measure the thickness, if you can see some differences in the or reduction in the thickness, it means that there is a sign of the plastic deformation. Okay, but brittle fracture, you don't see any changes in the dimension. Dimension is still the same, but the failure is catastrophic. Why? Because it doesn't show any plastic deformation. It's just a sudden failure. Okay, accidental failure. So that's the reason toughness is very important. It will absorb the energy, impact energy, especially, right? Okay, imagine the vessel, okay, being hammered by very hard materials, okay, hard tool, hammered by the hard tools, and without the plastic deformation, it will immediately fracture, okay, because of the brittle properties. But with the plastic deformation, the vessel, let's say this is the vessel, you may see some plastic deformation due to the hammered, okay, macam dia kena ketuk kan. Without the plastic deformation, it will suddenly break. But with the plastic deformation, it will show some changes in the dimension. So you know there is some destruction on the preservation. So you can take a further precaution. You can have a some time to release the pressure and do something to repair the preservation or to replace the preservation so that you can avoid explosion. So that's the reason these properties are very important. Very important. Okay, you need to eliminate brittleness because it will easily forming crack on the any engineering method. Okay. Okay. So we are talking about tempering. It is very important process. The heating will be the heating process in the tempering will be done below eutectoid temperature. What is eutectoid temperature? Still remember from the um, uh, iron carbide. Okay, first diagram. So this is the point for eutectoid temperature, and this is the line for eutectoid temperature, which is 7 to 7 degrees Celsius. Okay, so for the tempering process, the temperature for tempering is below than this temperature. Okay, so meaning that there's no transformation into austenite phase. All right, this process will soften the martensite by transforming it to structure of iron carbide particle in a matrix of ferrite. Okay, so reheating steel tempered microstructure. The reheatings quench still allow diffusion of the interstitial trapped carbon and hence reduction of the lattice strain. Okay, this is microstructure of tempered steel for the hyper-eutectoid steel. Okay, this results in softer and tougher materials. All right, if we look at when we conduct the tempering process, there are several parameters need to be considered because if you want to optimize the properties, you can refer to what a parameter that you can play. Okay, sometimes the time, the duration of the tempering process. Sometimes you can optimize the properties. Okay, we talk about these properties. Okay, by tailor the temperature of tempering process. Okay, so in this figure, it shows how properties can be influenced by the tempering temperature. Okay, higher temperature with longer tempering time will produce steel with higher toughness, but not always. Okay, not always. Okay, too high temperature, okay, like 800 degrees Celsius, will reduce the strength and perhaps it will reduce the toughness. Okay. Lower tempering temperature will retain a lot of more martensite, therefore steel will be harder than the longer or higher temperature of tempering process. Right. Okay. One more thing. When we talk about retain the hardness properties, so we can get benefit from this property for better wear resistant. So meaning that if the structure will not serve for impact load, just for meaning that there's no impact load involved, so you can utilize the hardness for a wear resistant. This is important for the engineering component that always experience friction load. Okay, so this there are pros and cons when you increase the temperature or prolong the tempering process. Okay, so in the summary, in simple terms, heat treatment is the process of heating, holding at the temperature, okay, heating, holding, and then cooling, right? So if you look at the cooling, the temperature profile, temperature versus time, okay? You just need to heat, soaking, and cooling. The time is important, the temperature is important. The cooling rate also important, whether very fast, slow, very slow. Okay, cooling rate will determine the final microstructure. Okay, during the process, the high temperature alter the microstructure of the metal. Okay, And microstructure plays an important role in mechanical properties of materials. Okay. The final outcome of heat treatment process depends on many different factors. Okay, this include the heat treatment temperature, the time, okay, and the rate of cooling. Okay, I have already mentioned this. Okay, remember this diagram: temperature versus time. Okay, heating at what temperature, and then soaking how long, and the cooling rate, whether it is slow, moderate, or very fast. Okay. Right. If we compare in terms of the microstructure, all right, this is how microstructure process influence microstructure as well as the properties. Okay, by heat treatment, okay, if you look at the slow cooling, right, there are process involved, which is we call it annealing and normalizing. It will produce polite and a proitated phase. Okay. For the rapid in the quenching process, okay, we can get martensite, which is brittle or hard. Okay, and this we will obtain such as the polite, which is soft or ductile. Okay, depending on the carbon content. But this one is moderate. This one is in between the polite and martensite. Okay, so this can be adjusted depending on the size and the process. The difference is only microstructure. Okay, you can adjust the cooling rate. Okay, whether it is very fast, moderate, or very slow. The moderate, you need to adjust what is the degree, the temperature reduction over the time. Okay, so the microstructure, okay, higher strength for the martensite or higher hardness, and very high ductility for the spheroidite. How we got spheroidite? This is only for hyper-eutathon. Okay, hyper-eutathon alone. This modified of polite structure into a spherical microstructure will obtain the highest ductility of the steel. Okay, we talk about steel, only steel. Okay, this is only the heat treatment for the steel. But the heat treatment also, this heat treatment also can be done for any other non-ferrous alloy. Okay, for example, aluminum alloy and many others. Okay. All right. Any questions so far before we move to the next lesson? Tak ada soalan eh? Okay. Kalau tak ada, kita move to the next slide. You all dengar ke? Ke saya dah terkeluar ke macam mana?
Dengar.
Okay, very good.
Dengar je.
Sorry terdengar background anak-anak saya ni sekali. So, sabarlah ya. Alright. The next lesson, okay, hardening, isothermal hardening. Okay, this one is basically if you are working in the industry involving steel, this one is quite important. Okay, I can say it is very important. All right, so at the end of this course or this lesson, you should really understand the isothermal phase transformation. When we talk about isothermal, meaning that we conduct the heat treatment involving holding at a specific temperature, one single temperature, okay, and allow the transformation process occur at this particular single temperature. So isothermal, satu temperature sahaja, okay, and at a holding temperature, it will change the microstructure. The phase transformation occur at this one single temperature. And also involve the formation of binite microstructure, because this one I haven't yet explained in the previous lesson, and then explain the other two tempering process we call Marr tempering and Aus tempering. Okay, what is isothermal? Okay, isothermal hardening is a heat treatment process for plain carbon steel, where it is done by heating the steel until it becomes austenite. Okay, I have explained this earlier. Okay, we let it transform into FCC structure first, which is in the form of austenite, and then quench. We do the quenching, not necessarily at the room temperature, not necessarily involve water, but there are some solution with a specific temperature. Okay, specific temperature. We hold at this temperature and left there for a specific span of time before we cool it at room temperature. Okay, we allow the phase transformation at this isothermal temperature. Okay. During this heat treatment, the microstructure transforms into a combination of different microstructure. We can customize what temperature, what microstructure that we want. If we want the mixture between martensite plus perlite, yes, we can. We want it to be 10% and 90%, yes, we can. Okay, this is where we can tailor our product, our engineering component. We can have whatever the portion. We can have it 50% martensite and 50% perlite, because we know this is hard. You want to increase more martensite and half of it is perlite. Or if you think that after testing the product, you think less hardness, you can further increase to 70% and 30%. Yes, of course you can. Okay, this is the process where you can tailor your microstructure of the product. Okay, so method for determining isothermal transformation. Okay, before, okay, of course, if you are working in Malaysia, in any industry involving steel or any steel maker company, you don't have to think about this so much. This is the history how the transformation occur. Okay, all right. People start with experimental work. Okay, before this is the job of the steel supplier. Okay? Let's say they have steel containing 0.8% carbon. Right? They test. Okay, this is new steel. It's contains 0.8% carbon. I want to know what is possible isothermal reaction can perform on this steel. So you are the producer of the steel of this new material. Okay. So first, it is being heated in the furnace. Okay, and of course, at the austenite temperature. So depending on the composition, you need to refer to the phase diagram. Okay. All right. The austenization process is highly depends on the temperature. You need to know for this steel, there's a 0.8% carbon, what is the temperature to obtain austenite phase. And then after some time, so holding at this austenite and ensuring that all the microstructure inside the steel is transformed into austenite. This is austenite. Okay, right. And then choose one single temperature, which is below than austenite temperature. All right. From this first sample, you quickly transform into this furnace that containing that particular temperature. Okay. For example, this is 900 degrees Celsius. Okay. And you take all right. Let's say this is 723, and this is 0.76. This is temperature versus carbon percent. All right, so let's say this is a 0.8%, and this is temperature 740 degrees Celsius. Okay, so to achieve alternate phase, and of course at this bottom, this is alpha plus cementite. Okay, right. So now you want to you want to ensure that it is 100% transformed into arsenide. So you need to choose this temperature, which is 20 to 50 degree Celsius above this line. Okay, so let's say you choose this temperature. Let's say this is the limit. So you choose to achieve arsenide, you take 760 degrees Celsius. Okay, this is the temperature. Okay, now let's say this is 760 degrees Celsius. So slightly below than 7 for temperature below than the arsenide. So the temperature for arsenide for this 0.8 is 740 degrees Celsius. Okay, so for the first experimental work, you can choose temperature below than this temperature. Let's say you take 730 degrees Celsius. Okay, so meaning that from the 760 to 730 degrees Celsius, okay, you put it into this furnace, and then after, let's say, for example, at this temperature, let's say 0.3 seconds or maybe 1 second. Okay, whatever the time, you need to investigate, run the experiment for a series of soaking time inside this temperature before you can quench into a cold water. Okay, room temperature, 25 degrees Celsius. Okay, first sample maybe 0.3 second, second sample 1 second, third sample 5 seconds. It depends on the your observation. Okay, so this is the phase diagram. Okay, okay, sorry. In this example, we use 0.8% carbon. Let's say this is the composition of your alloy, and then you take above 7 to 7 degrees Celsius to achieve arsenide temperature. And then, so this is what happened, right? Firstly, you heat it up to this temperature, and after 6 seconds, okay, let's say this in this example, 6 seconds, you quench at this temperature, which is 700 degrees Celsius. Okay, this is first experiment. First experiment at 700 degrees Celsius. And then the first one, sample number 1, after 6 seconds, you quench into cold water. You can see there are small amount of, what is it? Perlite. And then again, let's go to this one. Okay, and then this is sample number 1. Sample number 2, you take 18, okay, 18 seconds, right? At this, after 18 seconds, you can see more perlite. 20 seconds, sample number 3, you holding at 700 degrees Celsius, okay, for 22 seconds, and then you cool it down into room temperature by quenching in the cold water. Okay, after 22 seconds, you can see more perlite. Then, if you prolong the soaking time before the quenching to 24, you can see more microstructure of perlite. And then it is completely transformed into the 100% perlite. Is at 67 second soaking at 700 degrees Celsius. See, okay, soaking time, holding at this particular temperature, okay, will influence the transformation. So this transformation occur at 700 degrees Celsius. Okay, this is the first isothermal temperature. Okay, using the isothermal data at 700 degrees Celsius, which is the first temperature, identify the start and the finish times of the isothermal of the transformation. Okay, right? So this is temperature 1. Okay, the first and the last. This is what the steel maker will produce the data. The first, they take one temperature and see at what time that the first transformation into polite, okay, formation of polite. Right. So, and then at what temperature that they see the polite is 100% transformed. Okay, they record these two. And then using the same method at a different temperature. Okay, all right. Using the isothermal data at T2 to identify the start and finish time of the transformation and see is it still a polite or other microstructure. Okay, and then plot the start and finish time to develop the C curve or TTT diagram. Okay, this is the C curve. Okay, or we call it time temperature transformation. Okay, time temperature transformation. TTT diagram or C curve diagram. So this is uh, the data that provided for one single steel. In this example, 0.8% carbon. So let's say you produce new carbon steel, which is 0.9. You need to do the same. Okay, there are various temperatures, 1, 2, 3, 4, 5, and various temperature. Okay, to ensure that the data plot is following exactly the curve. You can okay. So the beginning of transformation, okay, the fraction of transformation, from 0 meaning there's nothing, and or maybe 1%, we can say it is starting point. Okay, starting point, the fraction of transformation, meaning that let's say it is a formation of polite. So the beginning of polite, the time. This is the time. Okay, right. So the first point we plot here, and the 100% of polite formation will be plotted here. Okay, and second temperature here and here. Okay, and then you will plot the graph, and this is the final curve. Okay, of course you need to do various temperature to ensure what is the microstructure that you obtain. Okay, right, not just two, because let's say you choose a two temperature, one is 700 degrees Celsius and the second temperature T2. How to determine this one? Okay, you can only this point can only be obtained after you conduct a series of uh, uh, soaking temperature, soaking time, series of time. Then only you can see this pattern. Okay. Right. So if we are looking at this DC curve ataupun TTT diagram, isothermal transformation diagram. Okay, so the microstructure, if you choose temperature around 700 to 600, okay, you can see from under microscope, you can see they are different between this range of temperature and this one. If you look at under microstructure, you can see here is a coarse polite. You can see 100% polite, but compared to this one, it is very fine polite. All right, anybody can tell me why they are different in terms of the size? Sorry, size I'm sorry. Okay, okay, coarse polite. They are all polite. And then the fine polite. This is fine polite. Okay, so do you know why they produce fine polite? compared to the higher temperature of soaking or isothermal temperature. High temperature, low isothermal temperature. Why? Anybody?
Temperature difference.
When? From when? From what temperature to what temperature? From what temperature to what temperature? Temperature difference. Okay, sorry. I don't know what do you mean by temperature difference. Okay, so how temperature influence the difference in terms of the microstructure? Any idea? How the fine sunlight obtained if we choose isothermal temperature lower? For example, we take this one at 550 degrees Celsius and this one is 650 degrees Celsius. Okay, do you know why? Any idea? Think.
To get fine per light, we cooling.
Cooling from where? From what temperature to what temperature? At what? At what? At what stage? Cooling during what? Come on, this make me understand what you are trying to deliver. Oh, slide nombor 7. Saya nak ambil masa. Hello.
Tak pasti, Doktor.
Okay. Alright. Susah Okay. Dia terlampau kompleks. This is engineering complex. Lepas tu nak jadi engineer ni you kena serabut sikit. Kompleks lah. Right. Okay. If you still remember, okay. Right. During the process, we do for this one. Okay. This is the temperature where we want to ensure that we still having arsenite. Okay, arsenite. At the equilibrium reactions, you can have arsenite transform into perlite. Okay, equilibrium means that it will naturally diffuse by over the reduction of temperature. Okay, semasa sejuk tu, naturally dia akan forming perlite, right? But the perlite size, the grain size of perlite might different if you change drastically, okay, to this temperature, not to the room temperature, but from the, let's say, 740 degrees Celsius, you change it into 550 degrees Celsius. Okay, it means, imagine 700 to 550. It is a big sudden changes. Okay, within a second. This one also called quench. Okay, for the 200 degrees Celsius reduction within a second. Okay, within a second. So what does it mean? There is some quenching effect. Okay, if you reduce to 650, maybe it's not really sudden. It is just 100 degrees Celsius per second, about that value. Compared to this one, it is 200 degrees Celsius per second. Okay, large temperature difference. It is more rapid cooling compared to this one. Not really rapid, but faster cooling compared to the first one. See? So because of the cooling rate, okay, the changes is very fast, not to the room temperature. I'm not talking about changes to the room temperature. Quenching is not necessarily to the room temperature. This is also calling quenching, okay? So meaning that you immediately change. You do not, okay, so this is what happened. So because of it is high temperature, 546, 650 degrees Celsius, so you don't see martensite, okay? You don't see martensite. You will only see martensite if, okay, if you achieve this range of temperature. So now it is only 600 to 550 degrees, to 550 degrees Celsius. So what you can see is only perlite. So now you know, okay, if you want to have coarse perlite, all right, let it cool slowly like annealing process. This is normal annealing process. Okay, you don't need this process. Okay, but if you want other microstructure such as lower bainite and martensite, you need to know what is temperature. Okay, for example, if you want to be martensite, you need to very fast cooling for less than 1 second. This is the time. Okay, this is the time. So your cooling process to this temperature, okay, to achieve 200 or completely finishing MS, referring to finish formation of martensite, less than 100%, you need to achieve this within less than 1 second. Okay, less than 1 second. This is low. Okay, so if you want to have lower bainite, you can do it first heating to the austenite phase and then quench to this one. And then hold at how long? Maybe 10,000 seconds. Okay, you hold it at this temperature for a certain period of time until it is passing this line. If it is more than 1,000 seconds, meaning maybe 2,000 seconds, it is 100% completely transformed into lower bainite. Okay, there are another microstructure, upper bainite. Sometimes it is mixed between upper bainite and fine perlite. Okay, so if you want it to be to obtain fine perlite, you can quench to this temperature and hold it after 10 seconds or maybe 20 seconds to be safe. Okay, maybe 50 seconds. And then after that, you can quench to room temperature. Then your microstructure will be fine perlite. Okay, compared to if we compare fine perlite and coarse perlite, right? What is the difference in terms of the mechanical properties? What is the difference between these two? Coarse perlite and fine perlite. This coarse. What's the difference?
Fine perlite undergoes plastic deformation.
Okay. What about the coarse pearlite? It doesn't experience any plastic deformation.
Cospelite exhibit a structure discontinuity upon deformation.
Discontinuity. What makes you say it's a discontinuity? What does it mean? Discontinuity.
I don't really know, Doctor. Google.
Oh, all right. Okay. If we relate to the chapter 3, 4, central mechanism and mechanical properties, all right, it is straightforward saying that coarse grained versus fine grained, isn't it? Am I correct? So if we guess the mechanical properties between these two, what mechanical properties are different between these two? Okay, just now you mentioned ductility. Okay, which one is more ductile?
Coarse.
Coarse, yes. So coarse pearlite is softer than fine pearlite. Okay, because of the grain, the grain. Okay, finer grain means containing higher amount of grain boundary. Okay, higher obstacle to the dislocation motion. So they are all interrelated. Sebab tu you all belajar central mechanism dalam chapter awal. Yang ni kemudian. This one is application on the first 4 or 5 topic. Okay, which is really fundamental. This one is just application. Okay, the application is one of it is a strengthening mechanism. Okay, you reduce the grain size, even you still obtain the same microstructure. You still obtain pearlite. Okay, the faces is still the same. Fasa dia masih lagi sama, dua-dua pearlite, tetapi changes in terms of the grain size. Okay, so in this case, you don't change the carbon content. Of course, if you put more carbon, you can increase the strength. No, in this case, you don't need to alter the chemical composition of your alloy. What you can do, you just reduce the size. Okay, you still want to have pearlite, 100% pearlite, because pearlite is tough, but you want it to be more tougher, you just reduce the grain size. Okay, then you can get whatever the properties you want. All right. So the formation, okay, inside the austenite is formed the pearlite colony, and then it grows. This is normal behavior of the diffusion, okay, or solidification or any phase transformation. Okay, in this case, the changes from austenite into pearlite happen at the solid state. Okay, so what happened inside this the changes transformation in the solid state is the carbon diffusion. Okay, carbon diffusion because carbon is very small, lightweight, so it will move easily. Okay, inside the crystal structure of the iron. Okay, it will move and rearrange themselves to form pearlite, and the longer the time, okay, the larger the amount of pearlite. Okay, and the process continues. Right. So so this is the time. Okay, look at this. This is the time. Okay, so you need to choose wisely what is the time if you want it to be 100% pearlite. Okay, or if you want it to be, okay, the middle might be the 50% of transformation. So if you want to have only 50% of pearlite, so you stop at 100 seconds. Okay, don't go for 1000 seconds, because if you go until 1000 seconds, means you don't have normal austenite. Okay, austenite completely transformed into pearlite. So there's no more austenite. If there's no more austenite, whatever the changes you made, it will be unchanged, remain unchanged. Okay, so you need to know what time is suitable if you want it to be a certain fraction of whatever phases that you want. Okay, so this is pearlite. at a different quenching temperature or isothermal temperature, right? Further reduce the temperature, see, larger and smaller, the grain, okay, and so forth. All right. Next is the formation of binite. Okay, binite is a slightly faster cooling rate during the soaking at the isothermal temperature. So binite microstructure consists of non-lamellar mixture of the ferrite and carbide. Okay, so the higher holding temperature gave rise to what is commonly called upper binite, and that lower temperature called lower binite. Okay, so upper binite is not much different structure compared to the pearlite actually, and lower binite you can see they are very fine, okay, fine composition of what we call it cementite. Okay, remember cementite or if there is a large space of ferrite. So this guy, the white, this guy is associated with soft. Okay, if you have this kind of microstructure, this softness of ferrite properties will be dominant. Okay, but if you have this kind of microstructure, okay, which is the area of clean ferrite is less. Okay, you can see that ferrite is being packed with the small fraction of cementite. So this microstructure shows a tougher microstructure. Okay, so I should stop right here because it's already 4 o'clock. Okay, so lower and upper. If we look at this first see curve diagram or TTT diagram, this one is softer, this one is lower, is harder. Okay, in between, okay, there are increase in terms of the hardness from the coarse pearlite to the martensite. So this one is soft, and the bottom is hard or strong. Okay, so you can choose whatever your microstructure that you want. Okay, so binite basically will dominated at this range of isothermal temperature. Okay, let's say from the austenite region, and then you holding Holden temperature beyond the 2000 or 3000 second. Okay, basically we take longer than this limit, and then quench to room temperature, or you can cool it slowly or whatever, because once there's no more austenites means that if you cool it fast or slow, there's no changes after that. Okay, this is the beginning of transformation. Okay, this is the point where it starts to form lower binite, and then this is a point where the ends of transformation into lower binite. Okay, so I think I should stop here, right here. We will continue tomorrow, and tomorrow also please do not contact, okay, do not skip for tomorrow's class, because I'm going to explain the group assignment. Okay, group assignment I will publish in the e-learning, and I will explain tomorrow. Okay, you are going to have about 6 weeks to complete the assignment. Okay, all right, any question before we end our class?
No,
If you
Doctor.
have okay, good. If you have no question, I think that's all for today. And if you haven't signed the attendance,
Kasihan dong. Kamu lagi tadi video.
right, if you haven't yet signed the attendance, please scan this QR code. And if you are done, I think thank you so much, and see you again tomorrow. All right.
Thank you, Doctor.
You're welcome.
Thank you.